is Dr. Sridhar, back to you with another video session on three-phase induction motors. This three-phase induction motor is asynchronous motor. It never attains the synchronous speed. What is synchronous speed? This is the maximum speed that revolving magnetic field will achieve. So we don't know about this revolving field and synchronous speed. Generally, there is a formula is used to calculate the synchronous speed, that is 120 into F by P. So 120 is a constant, F is nothing but the frequency and P is nothing but the number of poles. This speed is normally it is called as a synchronous speed. This is the synchronous speed. This is the maximum rated speed the motor can achieve or try to achieve. So 120 into F is nothing but the frequency of the supply. So suppose if the frequency of the supply is 50 Hz and if number of poles are nothing but the 4. So this is 120 into 50 by 4. So this is 1500 RPM is nothing but that is the synchronous speed. So this is the method used to calculate the synchronous speed. But the induction motors are widely used in the industries. Three-phase induction motors are the most common and frequently encountered machines in the industry, and simple and robust, low price and easy maintenance. So, and technically if you're speaking, these induction motors always runs at commercial power factor is 0.8 power factor lagging. So induction motors runs at 0.8 power factor lagging, and its speeds depends on the frequency and the power source. Just now also we have discussed that the speed of synchronous motor depends on the frequency. It is not easy to have variable speed control, but there are some frequency control methods are available and speed control methods are also available, but a little bit some accessories we had to connect to control the speed of a induction motor. But in the commercial DC machines, if I am speaking, in the DC machines, now by changing minimum things, you can regulate or you can control the speed, but in the three-phase induction motors, it's not possible. So there are other methods are available. With the help of those speed control methods, it is possible to control the speed of the three-phase induction motor. So it is run essentially as a constant speed from no load to full load, but it never runs as close as possible to the synchronous speed, but it never attains the synchronous speed. Once it attains the synchronous speed, the motor will comes to rest, because always the rotor always search for it always behind the synchronous speed, never it attains. So that is the logic, that is the beauty of the three-phase induction motor. So three-phase induction motor, there are if you are speaking about the construction, now there are two major parts are there. That is one is the stationary part, that is nothing but the stator, and next one is the rotating part, that is nothing but the rotor. So if you could compare the DC machines and the AC machines, now the starter is nothing but it is a stationary device, and this is the term it will be used in the induction motors or in the synchronous motors. It means in the AC machines. In the DC machines, field coils, that field coils are nothing but those are more or less same as the starter. Now it consisting of steel frame that supports a hollow cylindrical core, and core constructed from stacked laminations. Now that core also allows some air to flow inside to gather the excess amount of temperature it will be generated, or whenever you are laminating or stacking laminations are provided in the outer surface by slots or something else, now it will be acts like a agent for cooling media. So whenever it allows some air to pass onto the body, now it will extract some amount of temperature, it will be generated from the starter windings. So this is the one mechanism, and next one is the revolving rotor. Now rotor, it is a revolving body. It is composed of punched laminations stacked to create a series of rotor slots, providing space for the rotor winding. Now here rotor is also, again there are two types of rotors are there, squirrel cage induction rotor and slip ring rotor. There are two types of rotors. So based on the rotors types, induction motors are classified into two. One is the slip ring induction motor and next one is the squirrel cage induction motor. So squirrel cage means why the name came to that particular rotor means, if you could observe the rotor of squirrel cage induction motor, it will looks like a cage. So additional of resistance or removing of resistance or controlling some of the parameters is Not possible. Once if it built, it's built. That's all. We cannot vary the parameter or rotor parameter or circuit parameters as and when it is necessary. So that squirrel cage induction motor is permanently fixed. We cannot alter any parameter, electrical parameter in the rotor circuit. But whereas in the slip ring induction motor, so you can add, there is a provision to add some external resistance. Now based on the requirement, suppose if the torque is not sufficient, so you can alter the resistance connected to the rotor circuit, and that provision is available in the slip ring induction motor. Now, but widely used induction motor is the squirrel cage induction motor only. Now, another name of this slip ring induction motor is wound rotor. So, the rotating magnetic field cuts the rotor windings and produces an induced voltage in the rotor windings. So, due to the fact that the rotor windings are short circuited, because just now also we have discussed that cage type of arrangement, squirrel cage induction motor, if you could see, the rotor windings are permanently short circuited. Once the permanently short circuited, whenever the magnetic flux passes from the north pole to the south pole, so from the starter coils, now whenever flux pass on to the rotor windings, now there will be a cutting of magnetic flux takes place, and with what velocity that magnetic flux or starter flux is sweeps the rotor conductors means at the synchronous speed. Now that's why that magnetic field is called as a rotating magnetic field. And not only this rotating magnetic field will have a magnitude that is 3 to 3 by 2 times of pi maximum. That pi maximum is nothing but again it depends on the three-phase induction or three-phase supplies currents, that three-phase currents. So maximum times to the 1.5 times of the maximum flux, it will have its magnitude, that rotating magnetic field. And always this rotating magnetic field revolves in the air gap between the starter and rotor with synchronous speed. So with that much of speed and having some constant magnitude, if the flux sweeps the rotor, definitely there will be a cutting of the magnetic flux with the conductors. Now again the conductors are short circuited, means the induced EMF it will be generated. That induced EMF is easily finds the closed path as the rotor itself it is short circuited, so it drives some amount of currents through it. So once the current is flowing, so simply the rotor starts revolving in a particular direction. So that's why this three-phase induction motor is called as a self-starting device. So you need not provide any accessories to start the induction motor. So induction motor is nothing but it is a self-starting device. So because the torque was produced whenever the rotating revolving magnetic field sweeps the rotor, there will be induced EMF in the rotor conductor, and the rotor is short circuited on itself. So certainly there will be a current. So this current and the main current, rotating magnetic field current, it will be interacted to each other. Once the existence of interaction takes place, then from there onwards, rotor starts revolves in a particular direction. That is nothing but rotor experiences a torque. That torque is nothing but that because of the torque only that motor becomes it is a self-starting device. So that is a one important point. Always the three-phase induction motors are self-starting devices. So what is the speed that induction motor will always have? So always, as just now we have discussed, the rotor tries to reach the synchronous speed, but it never attains. Once it attains, then induction motor is not a induction motor. That's why this induction motor is called as a asynchronous motor. Always the speed of the rotor is lesser than the synchronous speed. How much it will be less? That is nothing but the difference between the motor speed, that is the rotor speed, and the synchronous speed is called as a slip. So how much of difference between the synchronous speed and the motor speed, that is nothing but it is called as the slip. That slip speed is nothing but the difference between synchronous speed minus motor speed. That is slip speed is nothing but the n slip. It is always the difference between synchronous speed and the motor speed and the rotor speed. The rotor speed is nothing but that will be calculated across the shaft. So one more important point here, slip. That is a very, very important point we have to remember. What is the slip? Slip is nothing but the difference between the synchronous speed and the motor speed to the synchronous speed. This is the formula it will be used to calculate the slip of the induction motor. So there are two cases are there. if the rotor runs at the synchronous speed. Of course, it is not possible, but ideally, if you are speaking, if you are assuming the rotor attains the synchronous speed, rotor speed and synchronous speed both are same, then the numerator becomes same. So numerators parameters are same. So slip becomes 0. If the rotor is stationary, if the rotor is not at all achieving, so why I am taking these two impossible cases means, now with the help of these two simple assumptions or two simple cases, we can predict what could be the minimum value of the slip and what could be the maximum value of the slip. If the rotor is at stationary condition, so this particular value is 0. So n synchronous to the n synchronous, it will becomes 1. So slip may be expressed as a percentage by multiplying the above equation. And what could be the values of the slips means, so minimum value is 0 and maximum value is 1. So there is frequency is also there, slip frequency. This is a rotor frequency. So rotor frequency and the starter frequency will be different. Why? Because a rotor is a revolving part. So this rotor, if rotor is not revolving, this three-phase induction motor is more or less same as a single-phase transformer. The difference here it is because of the revolving nature of the rotor. Now rotor frequency is different and starter frequency will becomes different. Rotor frequency, if you want to calculate, the rotor frequency is nothing but Fr is equals P into SNS. SNS is nothing but the slip times of the synchronous speed divided by 120 is nothing but the slip times of the frequency. So what is this Fe? Here it is slip times of induced EMF frequency. So that is the case here. So that's why there is a small difference is there between the starter frequency and the rotor frequency. Why the difference is existing means that the simple reasoning, the rotor is nothing but the revolving on itself. So this is the fundamental things we require to understand the three-phase induction motor. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.